All right, today we're going to start looking at rational expressions, applications of them, and that sort of thing. The first thing we need to talk about, though, is our first lesson, non-permissible values and simplifying. So if we're going to talk about rational expressions, it's helpful to take a step back and look at what a rational number is. Now, we talked about those in Math 10. So a rational number, the definition, it can be something that you can write as a fraction. So rational numbers are fractions that have integers for both the numerator and denominator. So they're fractions with integral, numerator, and denominator, but the denominator is non-zero. Okay, so we know we can't divide by 0, so if it's a rational number, we can't have a 0 in that denominator. Now we can write it a little differently if you want to use variables here. You could say a rational number is defined as P over Q, where Q cannot be equal to 0, and both P and Q are integers. Okay, they belong to the set of integers. Now you might see some people using I to denote that set, or Z, because there's a Latin word that stands for integer that I have no idea what it is, but Z is the other set that you might see. So it could say P and Q belong to the set of integers, or P and Q belong to the set of, well, integers. I or Z, take your pick, doesn't really matter. Okay, a rational expression then, as opposed to a rational number, is an expression written as the quotient of two polynomials. So now we've got to shift our thinking a little bit to involve some of those Math 10 concepts. Okay, so down below you have two examples of polynomials that are rational expressions. So you've got your quotient for both, polynomial, both top and bottom. Now the issue here, the denominators cannot be 0. But since I've got a variable inside both of them now, I've got x in the first one, but I've even got two variables in the second one, we have to make a restriction on that variable because I can't ever have the denominator be equal to 0. Okay, so that's what we're going to look at in this lesson. Okay, a rational expression cannot contain roots of variables or variables as exponents. So the following two expressions are not rational expressions. You've got an x as a variable exponent. That can't happen. In the other one, you've got a square root of x. That also can't happen in a rational expression. Okay, we're just going to evaluate these two rational expressions for these given values just to see what happens. A little bit of an investigation. So for the first one, that expression is 6 divided by x. We're going to take x to be equal to 2. So if I plug 2 into that, this will tell me I have 6 over 2, which is going to give me 3. So when x is equal to 2, I can evaluate this expression and get an answer that's okay. I can do that. What happens when x is equal to 0? Well, now I'm going to try to put 0 on the bottom of my fraction, and I can't divide that. I could try 6 divided by 0, and my calculator will tell me that I have an error, divide by 0. Okay, it might also tell you have a non-real answer, depending on your calculator. I'm not sure what some of them say, but this one says I've got a division by 0. That's a problem. So this, we could say error divided by 0 doesn't exist, whatever you want to say. This just gives me an error. Okay, if x is equal to 1, plug that number in, 6 over 1, that gives me 6. So the other two numbers are fine, 0 gives me the issue. Now we might expect the same thing to happen underneath, but we might see it works a little bit differently this time. So if I try the other expression, wherever I see x, I'm going to place in 2. So on the top, we're going to have a 3. Underneath, we're going to divide by whatever 2 minus 1 is. Okay, 2 minus 1 is just going to give us 1. And in this bracket, 2 plus 2. That'll give us 4. So the 1 from the first bracket multiplied with the 4 here, that'll be 3 over 4. Okay, that's totally acceptable. Those are two integers. This is a rational number. This is fine. I've got to do the same thing here for 0. So make all those x's equal to 0. So 3 on top again. 0 minus 1 will give you -1. 0 plus 2 will give you 2. So this one works out to be 3 over -2, so -3/2. Again, totally fine, 2 integers, that's a rational number, this is okay. But if I try to place an x is equal to 1, when you plug it into that first bracket on the bottom, it says 1 minus 1 now. Now that bracket will become 0. So 0 multiplied by anything along the bottom also becomes 0. Think back to quadratics and that zero product property we talked about. Very, very similar. So if I do this one, that's going to give me 3/0. And again, I'm going to get that error. Now, why'd that happen? In the first one in purple, when we plugged in 0, that's what made my denominator 0, which was a problem. But for the one underneath, if I use 0, we saw that that was okay. It was actually the value of 1 that gave us a problem. Okay, so it's not always going to be 0, but I am trying to find the number that makes the denominator 0. Now that number is going to change depending on the expression. Okay, now those values are what we call non-permissible values. The rational expressions are not defined for values of the variables that make the denominator 0. And we saw that that could change. Okay, those values are called non-permissible values. We cannot permit them to be inputted into our expression. Okay, we need to restrict the domains so we don't include those. Okay, example underneath, the expression x plus 5 over x minus 3 is not defined for x is equal to 3. So we can say that x equals 3 is a non-permissible value of this. It's not allowed. Now you might be able to think about this already, but let's go see what that graph looks like. I know it doesn't talk about it in here, but the graphs end up being quite interesting. So if I do x plus 5, I divide it by x minus 3, we can see what that graph will look like. Okay, it looks very, very strange. You've got this weird curve happening bottom left. You've got the same kind of curve happening top right, and this vertical line that goes straight down through the two pieces. Now that line is going to be the line straight through the center of this graph. Now it looks off-centered based on our window settings, but it actually goes through your non-permissible value, which is pretty cool. You can kind of see it from that. Hopefully you can see it from your table of values. But when x is equal to 3, it even tells you you've got an error. There isn't anything there, but the calculator shows you that vertical line there. Okay, that vertical line, it's called an asymptote. So that word will come up again and again as you keep studying math. But basically what it means is your function or your graph, it doesn't exist at that point. So your graph technically will never cross that line. It'll get infinitely close to it if I kept zooming out on either side of that line, but technically there's no data there. There's no points because if x is equal to 3, that's where we get a 0 on the bottom, and I can't divide by 0. So it is pretty interesting to think about. If you want to see the graph differently, go to Desmos, and you can graph that, put it in some different colors. You can zoom out and stuff, and you'll see that vertical line won't be there. But we'll talk about the graphs maybe in a later unit. I believe we talk about it when we do reciprocals. It comes up later. Determining non-permissible values is a whole other story. So if we look at this, I'm basically just going to look at the denominator and try to figure out what value makes it equal to 0. Now, sometimes you can do it just by inspection, by looking. So, of course, if you look at the first one, if I place in 0 for x, 0 minus 1 will give me -1. That's still okay. So 0 is not my NPV here, my non-permissible value. But if I plug in 1 for x, 1 minus 1 will make the bottom equal to 0. So just straight up by looking, x equals 1, that's our non-permissible value. Okay, if I do that for b, it's a little bit more tricky. I've got a quadratic equation or quadratic expression now underneath. I'm going to have 2 non-permissible values here, and I know that because when I tried it, I could do factoring, I could do quadratic formula, I could graph it and find the zeros, whatever it is you choose to do. There's going to be 2 solutions for x. So I have to remember all my factoring rules because they're all going to come back here and be super helpful. So yeah, I'm going to look at the constant and try to find 2 numbers that multiply to -6. Those same 2 numbers have to add to the coefficient of your x term, in this case, -1. So the 2 numbers that will do that are some combination of 3 and 2. Now, if my middle term is negative, that means my larger one has to be my negative value. So my 2 numbers are going to be -3, +2. That way, when I combine them, they combine to give me -1. Oh, excuse me. So if I factor the bottom, this will now say x squared plus 2 over x minus 3, x plus 2. Okay, now I've actually got to find the values that make each of these 0. Now this should sound really familiar. This is exactly what you did to try and solve a quadratic equation before. So let's take each of the factors, make them equal to 0, find the x-intercept, the zeros, the values that make the bottom part 0 here. Now, if you do each factor separately, this first one will tell you x is equal to 3. The second one tells you x equals -2. Now, if x is either of those numbers in our original expression, that will make my denominator 0. I don't really care about the numerator. I can always have 0 on the top. I can never have it on the bottom. So let's just test it out. If I do 3 squared, I get 9. 9 minus 3 is going to give me 6. 6 minus 6 will give me 0. So if x is equal to 3, that zeroes out the bottom. If I try that here, -2 squared will give me +4. +4 minus -2 will give me +6. And again, same scenario, 6 minus 6 equal to 0. So these are my two non-permissible values. Now you might see them written like this, or you might see it show up that x actually can't be equal to -2 or 3. Either one kind of tells us which our non-permissible values are. So either way, -2 is our non-permissible value. So x can't be that. If you're just looking for your non-permissible values, x is -2. That is the non-permissible value. So however you choose to represent it. Now for C, we could try to do the same thing, but we're going to run into a little bit of a problem here. If I try to factor this, x squared plus 1, you might start to think difference of squares. The issue, there's not actually a difference here. This is a sum, and we don't have a rule for a sum of squares. So trying to factor this is going to prove to be quite difficult. So let's just think about this, just looking at the denominator. Now, if it's x squared plus 1, no matter what I put in for x, the instant you square it, it becomes positive. And as soon as you add 1 to a positive number, it won't ever get to 0. It won't happen. Now, there's no way for me to get a negative, or a 0, I should say, sorry, on the bottom here. Because even if I put in 0 for x and I square 0, 0 squared is 0, plus 1 is 1. Now, if I put in -1, -1 squared is 1. 1 plus 1 is 2. There are no non-permissible values here. There isn't a number that I can put in for x that would give me a problem. Okay, so here you could say that x can be any real number. There is not a value x cannot be. Okay, x can be anything, doesn't matter. For D, let's go factor that one as well. And again, we really only care about the bottom. I know I could factor the top here also. That won't really help us yet to find anything. We just need to figure out what values x can't be. So let's factor the bottom. I need two numbers that add to 1. Multiply to 1, add to -2. Those two numbers are going to be 1 and 1, both negative. Okay, so this is going to be a perfect square trinomial since those two numbers are the same. So I know now that my two factors are x minus 1, x minus 1. Now you could also write this as x minus 1 squared, since those factors are the same. Now, if I go to locate a non-permissible value, again, I'm really just looking at the individual factors here. The only value that I cannot have is 1. Okay, so we could say that x cannot be 1, or x equals 1 is a non-permissible value. However you choose to represent it is totally fine. So x can't be 1, or saying x equals 1, that is a non-permissible value. Those two statements say the same thing. Okay, however you choose to represent it. Okay, underneath we can talk about equivalent rational expressions, very similar to equivalent fractions or equivalent ratios like you learned before. So if we're asked if the following are equal and equivalent, let's take a look at this here. So for these three, we're going to try to show that they're equal or equivalent. Now, if I can simplify, I should. Now, if I look at the first one, I've got a factor of 2 on the top, factor of 2 on the bottom. 2 divided by 2 would give me 1. Essentially what happens is the 2's cancel, and I'm really just left with an x plus 1 over an x minus 2. And that's really as far as I can go. I can't really simplify here. I could state my non-permissible value, and we could say x can't be equal to 2. It's a good habit to get into. Let's go do something with the second one now, see if there is anything we can do. It looks like I've got factors of 2 both top and bottom. So if I take a 2 out on top, I get 2 times x plus 1. Same thing on the bottom, 2x minus 2. This is the exact same expression which we started with to the left. Now, I could simplify again, but nothing's going to change at all. Okay, and again, x can't be equal to 2 for the same reason as before. So those two are equal to each other. They're equivalent. Now we've got to check the third one. Now it looks a little bit more challenging because I got some polynomials. I got even a quadratic top bottom. I got to factor these. So if I look at the top one first, 2 numbers that multiply to 2, add to 3, that's going to be 2 and 1. So x plus 2, since everything's positive, x plus 1. On the bottom, that's a difference of squares. So we're going to have an x plus 2 and an x plus 1. That's not what I want to write. I want that to say x minus 2. Now I look good. Okay, on the bottom here, I actually have 2 non-permissible values. X can't be equal to negative 2 or positive 2. Because if I square positive 2, gives me 4, minus 4 is 0. But if I square negative 2, I also get positive 4, which when I subtract 4 from it, still gives me a problem. So here I've actually got 2 non-permissible values. However, the expressions are the same because if I multiply by x plus 2 on top and on the bottom, those 2 factors are the same, so I can cancel them out also, just like we did with the factors of 2. The only difference is I've got 2 non-permissible values this time. Other than that, the expressions are equal and equivalent. They say exactly the same thing. But when I go to check those non-permissible values, I'm always going to use the original. So if I didn't use the original expression to check that non-permissible values, I would only have the 1 on the bottom here from the x minus 2 expression. Okay, that would only leave me with positive 2. But if I plug them back into the original, technically there are 2. I just got to be really careful that I'm always going to use the original expression to do this. Other than that, those expressions are exactly the same. Okay, underneath, we can actually create new expressions by multiplying or dividing by the same monomial, binomial, whatever it is that you want to do, just like we did on the top. So essentially, by canceling out those factors, we're dividing by the same expression, the same monomial, the same factor, whatever it is you want to say. Okay, so we're going to take this and write a couple different forms of this rational expression. So if I look, top and bottom have the same factor of x plus 2. If I cancel both of those out, I get a new expression that says 3 x minus 4 on the bottom. These 2 expressions are actually equal because they represent the same thing. All I did was simplify, and it gave me the new expression. Now I could even create something new by multiplying top and bottom by the same thing. Now it doesn't matter what you multiply by, as long as you do the same thing to top and bottom, like when we did the conjugate for rationalizing a radical. If I multiply top and bottom by x, this would tell me I've got 3x on top and x times x minus 4 on the bottom. Both expressions mean the same thing because the x's can then cancel out. So you can create as many ratios or expressions as you want, whatever it is you need to do to fit your needs, as long as you do the same thing to the top and bottom. So you could divide, you could also multiply. Now the expression in blue and the expression that was originally in black, they mean the same thing. They just don't look like it. They just look different. So you could, again, try it out with Desmos, graph them, type it out, and you'll see that the pictures will absolutely overlap. Now, if you want to try it right now, let's just do a simpler one. So if I do x over 2, and let's change this, I'm going to multiply the top and the bottom both by, let's do 2, top and bottom. So actually, I take that back. Let's do 3. So if I do x times 3 over 2 times 3, that will give me 3x over 6. Okay, and you could even graph them just to check. So if I do the first one, x over 2, And I'll do another line of 3x, and maybe I'll just brackets there, 3x over 6, and press graph. I should only see one line. If I see more than one, then I've done something wrong. It doesn't look like I do. Everything's okay here. You'll notice the 3 and the 6 could actually simplify to give you a half, which is the same thing as before. So by canceling out, by reducing, you're doing the same thing. Okay, so that original expression should match whatever it is you've multiplied by your simplified expression on the end. Okay, they're going to be equivalent. Okay, let's look at how to simplify some rational expressions here. Now, this is going to look really familiar if you remember anything about exponents. The same rules apply. So we're going to divide both the numerator and denominator by a common factor. Okay, now I personally am not a big fan of doing it that way. You can if you choose. The rules show up here the same as they do for exponents. Okay, so we're going to see if there's commonality between all of the pieces here. So between 15 and 20, they're going to share a number, and they've got a 5 in common as a common factor. So we're going to divide both the top and the bottom by a 5. X squared on the top, x on the bottom, they have in common 1x. So we're going to divide x and x. Y's are common, so we'll divide a y. Z's, I can do 1z because the bottom one has got 1, whereas the top has 3. I'm limited by the lesser of the two amounts. So we'll divide a z on the bottom and the top as well. So we're going to divide by the same thing, top and bottom. And if I do the first one, numerator will give me 15 divided by 5 will be 3. X squared divided by x is x. Y divided by y is 1. So those two technically just cancel each other out. Z squared divided by z, z cubed divided by z will leave me with z squared. Denominators 20 divided by 5 will give me 4. X divided by x cancels. Y divided by y cancels. Z divided by z cancels. We made it that way. There's nothing else I can reduce. So this is now an equivalent rational expression to the original, just simplified. Okay, nothing else I could do top and bottom. I could do something similar for the second one, divide top and bottom by the same thing. I'm actually going to split up this into 2 fractions using our fraction rules that we learned in junior high. So the first piece will give me a 3x squared over 2x minus 8x over 2x. Now you can think about this as just subtracting fractions. Since the denominators, the bases are the same, I should be able to just subtract the numerators, which I can do, and it will take me back to my original expression. So this is good so far. Let's just simplify both fractions. Okay, so 3 over 2 I can't do anything with. It'll leave me with a decimal, and we don't like decimals anymore. Let's leave it as a fraction. X squared over x will just leave me with an x. So this will be 3x over 2. Now my second fraction, 8x divided by 2x. 8 over 2 is 4. X over x cancels. So really there's just a 1 there. So I'm going to have 3x over 2 minus 4. Now let's try to put this back together. If I rewrite 4 as a fraction with a denominator of 2, this will tell me I've got 3x over 2 minus 8 over 2. So as a final simplified expression, 3x minus 8, whole thing over 2. So I can put it back together as a fraction. You could leave it here. They're both technically equal. I think the last form is better. Gives you more of a sense of that this is a rational expression because I have a polynomial on top and bottom, whereas this one has it split into 2 pieces. So this format actually shows you better that it is a rational expression because you've got that polynomial top-bottom. Okay, we get into a little bit more complicated ones, but not by much if you remember how to factor quite proficiently. In order to do this and see what I could divide top and bottom in order to simplify, you have to factor it first. And you have to factor completely everything, top, bottom. So we need to find 2 numbers, multiply to 8, add to 6. Everything's positive here. It's going to be 4 and 2. So on the top, we're going to have an x plus 4 and an x plus 2. Underneath, that's a difference of squares. Square root of 4 is 2. So we're going to have an x plus 2 and an x minus 2. Okay, at this point, it's a good habit. I know we didn't do it in the other ones, but we should be looking at our non-permissible values. So here underneath, since it's factored completely, I can say now that x can't be equal to 2 and minus 2. If I plug in 2 into this set of brackets, 2 minus 2 is 0, that's an issue. If I use -2, -2 plus 2, this bracket becomes 0. Again, that's a whole problem for the whole bottom, the whole denominator. So these are my two non-permissible values. Now I can worry about simplifying. If you notice you have same factors, top and bottom, they can cancel each other out. So I notice I've got an x plus 2 and an x plus 2. So I can cross those out, divide them. My simplified answer, x plus 4 over x minus 2, and my non-permissible values are 2 and -2. Okay, fully simplified, nothing else I can do here. We can do something similar for the end. Now we've got, again, to factor that. Might be a little bit more work this time. Now if I go to factor this one, again on the top I've got a difference of squares. Square root the first term gives me 4. Square root the second term gives me x. Place different signs in between them. So if I go to factor the top, I'm going to have 4 minus x and then 4 plus x. I could flip this one around with no penalty. But for this one, I might want to think about factoring out a negative sign to actually leave my x positive in the front. We'll take care of that in a second. Let's factor the bottom first. Now this one isn't as straightforward because my number in front of my x squared term is actually not 1 anymore. So I've got to think about doing that decomposition method. Now I need two numbers that I'll multiply to 24, but add to 11. 8 and 3 seem like they'll work. Looks like I need both to be negative for this to work out. Yeah. So this will be 2x squared minus 8x minus 3x. That'll add to -11. And then my plus 12 is on the end. So if I do -8 multiplied with -3, that'll give me positive 24. So this is going to work just fine. So let's go ahead and make that change that I was talking about. So on the top, we can factor a negative sign out from the first term. What that's going to do for us is flip everything. So the 4 was positive before, it's going to become negative and go on the back side of this. So we could actually say that I've got a positive x now, a -4. The second term, if it's 4 plus x, that's the same thing as x plus 4. I'm free to flip that around should I need to. This just looks nicer. You could have left it the other way just fine. This is just more aesthetically pleasing. My variable comes first, my constant second. Okay, we've got to factor the bottom part as well. Now, if we've got 4 terms, we can group the first 2 together, the last 2 together. So I'm going to write out all the steps here. If you know a shortcut, then by all means, go for it. So the first 2 items, 2x squared minus 8x, go together. My negative sign is going to stay outside of the brackets, which means I'm going to switch the second sign here. So that's going to be a 3x minus 12. Continuing, we've got an x minus 4 and x plus 4. So on the bottom, factor out each group. Where am I? Factor out each group here. Common factor from the first set of brackets is going to be 2x. So if I take a 2x out, I'm going to be left with an x minus 4, which looks good. If I take a common factor of 3 out of the second set of brackets, I'm going to have, again, an x minus 4, which looks good. My brackets are the same factor. That's ideal. Let's keep going. So I'm going to have minus x minus 4, x plus 4 underneath. My common factor here is going to be x minus 4 now, so let's put that in. The numbers in front of those are going to go together, so 2x minus 3. Okay, at this point, the bottom's factored. I should be looking for those non-permissible values. So let's rewrite it underneath. I'm going to run out of space here. So negative x minus 4, x plus 4, bottom part, x minus 4, and 2x minus 3. My non-permissible values, I'm going to have 2 of them. One of them is going to be positive 4 from the first set of brackets, because 4 minus 4 will give me 0. So I can say x cannot be 4. For the other one, take 2x minus 3, make it equal to 0. So you want to find the value of x that makes it 0. And if I do that, it'll tell me that I'm going to actually have 3 over 2 for my other value of x. And if you're not sure how I just did that, take 2x minus 3, make it equal to 0, and you're just going to solve for x. So this will tell me 2x is equal to 3. Divide. X is going to be 3 over 2. So the value of x that makes that factor equal to 0 is 3 over 2, 1.5. Okay, so those are going to be my two non-permissible values. Now I can look at simplifying. Once everything's factored fully, now I see that I've got two factors the same, top and bottom. So let's go ahead and divide them out. So my final, most simplified, nothing else I can do answer is negative x plus 4 divided by 2x minus 3. You can leave the brackets or not. I just prefer them. I just think they look nicer. X cannot be 4 or 3 over 2. There is your simplified solution. Now, you notice that one was a lot more work than some of the other ones we've done. But if you remember how to factor, that is going to be the biggest skill here. So if you need some factoring practice, there is tons online that you can just type in factoring practice, and the first 4 links that come up will probably be more than enough to refresh your memory on that. So that's what we would talk about if we're talking about non-permissible values, finding those values of your variable that make the denominator 0. Okay, if I don't have those, everything else kind of falls apart and nothing else really works. So as long as you remember how to factor, you can find them quite easily. Hope that went okay. The next lesson we'll talk about multiplying, dividing some more. And again, you've got some extra practice ones underneath. That is from your yellow and blue workbook that you should have. And again, just remember to complete that Google form for us. And we're here if you need some help. Thanks for watching, and we'll see you next time.